Okay, here we are for, I hope, our last edition of Snow Blizzard 2016 home videos. I'm trying a new program, this front cam thing, because my camera broke. Too much use, I guess, right? Alright, here we go. So, solve the differential equation with the initial condition 0, 1, expressing your answer as an explicit function, y equals f of x. So firstly, please note, they don't tell me separable. They just say solve the differential equation. They do give me an initial condition, and they do want me to get y by itself. I have to recognize that I've got y over here on the x side, and that it needs to be moved over. So, the first thing I'm going to do is divide both sides by 1 plus y to the first, so that I'll just leave the x stuff over here. Now, of course, when I do that, I'll get 1 over 1 plus y, which I'm going to make 1 plus y to the negative 1. So I'm going to have 1 plus y to the negative 1 dy dx is equal to 2x e to the x squared. Then I'm going to anti-differentiate both sides with respect to x. And then I've got to use a little bit of u substitution. Now maybe you can just do this in your head because it's really not that bad. U substitution, right? If u is equal to 1 plus y, du is equal to dy. And over here, if u is equal to x squared, du is equal to 2x dx. So it's very straight up u substitution. So I'm actually going to be integrating u to the negative 1 du and e to the u du. Probably should have used different variables, right? U substitution and v substitution or something like that. U to the negative 1, of course, is ln, and I'm just going to go ahead and put the 1 plus y back. Whoops, sorry. Is equal to the antiderivative of e to the u, which of course for us was e to the x squared. And I'm going to wrap up my c over here. Now I'm going to go ahead and take care of the get y by itself now, this part. And I'm going to do that by raising both sides to the e, or e to the. And of course, remember when I do e to the all of this, then I'm actually going to write that as e to the times e to the c. And remember, e to a constant is still a constant. So I'm going to end up with 1 plus y over here is equal to e to the x squared times e to the c, right? And we remember that e to the c is just still a constant, so that multiplier ends up just as one big C. Now we talked about this in the last video, that that's a sad looking C, isn't it? That this is not, that it is a plus C, but because of raising both sides to e, that's how the c turned out to be a coefficient. And then of course I will just subtract 1 from both sides. Now I'll take care of my initial condition part. So I'm going to plug up here. I'm going to plug 1 in for y. And 0 in for x. Right, and e to the 0 squared is 0, e to the 0 is 1, and e to the 1 is just e. So c turns out to be 2e to the negative 1. So when I go back here now and say y is equal to 2e to the negative 1 e to the e to the x squared minus 1. Of course, this can be combined, right, because I have see the same base twice, multiplication in between, add the exponents. Note to self, change this problem. Too many e to this. Done. Okay, so we've learned to solve differential equations, and we've learned to solve differential equations with an initial condition. We've learned distance and displacement, and we've learned now to solve separable differential equations with or without an initial condition. So, what happens when I get a derivative that I can't anti-differentiate? Right? What if I don't know how? It's not in a form. No matter what I try with methods that we know in BC calculus, I can't anti-differentiate it. I would still really, really like to be able to at least see a picture of the solution. And that's what Euler's method helps us to do. It's an approximate the solution to a differential equation. And of course the assumption is then that this differential equation, I don't need to approximate it if I can actually solve the differential equation. So the assumption here is that this is a differential equation I can't solve. So instead of getting an actual solution, I will use Euler's method to approximate the solution. So this looks like a pretty harmless differential equation, and you're like, well, I can just separate this, right? So I'll just add y to both sides, so you get y plus dy dx is equal to x. Well, yeah, you go ahead. See what you can do with that, right? There is nothing that you can do with that by anything that we know how to do to solve that. So I don't know what graph those slopes come from, right? Because this is a derivative, right? The derivative of some unknown function y is the difference of each x and y coordinates. So there's some graph out there that exists that every time you draw a tangent to that curve, the slope of the curve is the x coordinate minus the y coordinate. What is that curve? So we're going to, again, use Euler's method to do that. And just for a little history, there's Euler. Poor guy doesn't look so attractive there. I don't know what the heck is happening on his head. But he was a beast. He is the reason why a lot of the notation that we think is just so normal and taken for granted exists. F of x notation he came up with. He's the one that decided of all the Greek alphabet letters, he wanted to use pi for the circumference of the ratio of the circumference and diameter of a circle. He came up with using e for his own last name, E, right? His last name started with E, so that's why he decided to name 2.7 Andrew Jackson, window wafer. This letter, the whole sum, this capital epsilon for sum. I mean, all of these ideas in mathematics were around, but he's the one that gave those ideas and those numbers, in the case of E, pi, and I, the notation that we're so familiar with. And of course, that's just notation. Excuse me. He did so much of his own mathematics. It is, he's a beast. And he, much like Beethoven, went blind very, very early in his life, and still produced a whole, just volumes of incredible mathematics. There you go, a nice quote by another famous mathematician, Pierre-Simon Laplace. Read Euler, he is the master of us all. Alright, before tackling that first derivative of, the differential equation x minus y, I'm going to go through Euler's method with a very, very simple differential equation that you do know the answer to, just so you can see that Euler's method does get you an approximation. So, dy dx is equal to 2x. So you know what this is, right? I can anti-differentiate both sides, and I know that the family of functions that has a slope of 2x is a parabola. I can move from the family of functions to a specific parabola with this initial condition. Remember this notation, y of 0 means that when x is 0, y is 1. So I need to get y by itself and anti-differentiate, which of course you could do very easily. Let's pretend I don't know. Right? So pretend you can't anti-differentiate. Pretend you can't solve that. Alright? So, I'm going to use, this is why lines are so important in previous math classes. Here's another application of the linearization formula, which, remember, the linearization formula is just the point-slope form of a tangent line. That's all it is. So there it is in its fancy form. Remember, the linearization of x is equal to the original y and the original x. That's the point of tangency. And then this is the derivative, y prime, at the point of tangency, right? That's all that says. This is no more than y is equal to y sub 1 plus m times x minus x sub 1. It's the same freaking thing, right? Sorry. So, this point is the initial condition. It's the point on the original. So instead of thinking of it as a tangent line in this application, think of this as the initial condition you were given. And don't forget, it is a point on the original. And remember, we're pretending the original is something I don't know what it is. Right? I don't know what it is. Now, that's a lie. Shh! I do know what it is. Right? I do know that this is a parabola. Right? But I'm pretending that I don't know. And this value is m, right? This is the slope at this initial condition 0, 1. Okay. So here we go. Given the differential equation and initial value, I'm going to Euler this. I'm going to use my linearization formula, and I'm going to get my first iteration, my first run through is, now think about where all these points came from. This is x sub 0, this is y sub 0, and this is the slope. Now how did I get that slope? I took my initial condition, x is 0, y is 1, and I plugged the initial condition into the derivative to get the slope at 0, 1. Now note, this derivative, this particular differential equation only depends on the x-coordinate of the initial condition, right? This derivative describes the slopes on a graph where the slope at every point is just 2 times the x-coordinate of that point. So I put in 0, and that's why I got 0. So of course the slope of 0 means I have a horizontal line, so this equation is actually y equals 1. So there I've simplified my first iteration. Y is equal to 1. Now, this is the linearization. The linearization, remember, if you zoom in on any function that is differentiable, and of course this one is, it has a derivative, right, 2x, of a function I can't see, I know is on that curve. Well, the curve approximates its tangent line at a point, right? Right? Local linearity. If you zoom in close enough, the curve looks like its tangent line. Well, I don't know what the curve is, but here is its tangent line at 0, 1. Then I'm going to use the tangent line to get me another point. Now remember, 0, 1 is on the curve I can't see. I'm going to use my tangent line to approximate a point on the curve, right? Because remember, a tangent line and its curve is equal only in one spot, and that's at its tangent line. If you move away from the tangent line just by a little bit, you're not going to be on the curve, but you're going to be close, right? So I'm going to choose a small change in x. I'm only going to move a small distance away from the point of tangency, which for us right now is 0, 1. And then I'm going to use the tangent line to get me a new point. It's not going to be on the curve, but as long as I have a small delta x, it will be close. And then I'm going to tell myself that that's my new initial condition. So here's what I mean by that. I am going to choose a small delta x to be 0.5, and I'm going to say, well, my initial condition was 0, 1, so if I move a distance of 0.5 away from that, my next point is going to be 0.5 comma something, right? Because I just added 0.5, change delta x, change by delta x, I should say. So what happens when you take 0.5 and plug it into the linearization? Well, since my linearization was just a horizontal line, the linearization at 0.5 would be the linearization at any value, really, which would be 1. This is my new point. Right? Take this value and put it here. And I'm going to consider that my new initial condition. Wink, wink. Right? This is fake. But it's a close fake. So now take this, consider this your new initial condition for x and your new initial condition for y. So my second iteration using Euler is the new y, initial condition. New initial condition, psych is not real. And then of course, where did I get the slope? Where do you always go for a slope in calculus? Slope goes with derivative. So up here, you're taking the point, 0.51, right? Your new fake point, you're taking this, and since this derivative only depends upon x, you're taking 0.5, plugging it in here, 2 times 0.5, usually 1. So there you go. This is your new tangent line. What are you going to do with the new tangent line? You're going to use the tangent line to approximate another point. So what other point are you going to use? Well, you're going to move another delta x, and you're going to say, well, how about 1? Using the second linearization, at 1, plug in 1, and what y do you get? So notice I have my same initial condition, right? Initial condition y of 1, x of 0.5, but this time in place of x, I'm putting a new x, 1, and multiplying by my same slope. What do I get out of that? I get 1.5. So I have fake 2, right? This was real. This was fake 1, fake 2. And of course I'm going to move another delta x. I cleaned, right? I'm gonna, here's my third iteration through, right? I have my new initial condition, right? I'm going to consider this x sub 0, y sub 0. So see here, you see it, x sub 0, y sub 0. Where did I get the slope? I used the slope formula, only depending upon the x. 2 times 1 gives me 2. Now I'm going to add 0.5. Oh, I ran out of room up here, didn't I? Add 0.5 and get 1.5, comma, I don't know what. So I'm going to plug 1.5 into the linearization and get 2.5. And there is my third fake. So I can keep going, but again, the farther I get away from the point of tangency, from the real, right, from 0, 1, the farther away each one of these approximations is. This is Euler's formula. And it really is just the linearization formula, but check this out. What's going on here? Can you figure out why this is here? What does this mean? So what this says is the next y that you want is equal to the previous y you had plus the slope using the differential equation you have at the previous x and the previous y times delta x, right? I thought that was supposed to be x previous x, or x minus previous x. Well, if you notice what happened each time, since I chose my delta x to be 0.5, every time I used my linearization and plugged in, I got 1 minus 0.5. Well, what is that? 0.5. Over here, look, 1.5 minus 1. What was that? 0.5. Right? So you're always going to end up with delta x here. Cute, right? So let me draw a graph of those points that we found. Remember, using just the differential equation and the initial condition 0, 1, and a chosen delta x of 0.5, and Euler's formula, I'm going to lay this out in a chart. And AP recognizes this chart as work shown. They know what you're doing. And students tend to like this a little bit better than running through the equation multiple times. So I'm going to show you how I get the same result, and I'm going to graph at the same time. So 0, 1, I plotted. There you go, 0, 1. That's my initial condition. My derivative at 0, 1 is 0, right? So take 0 and 1 and go to the derivative and plug in. Now again, this derivative only depends upon x, so you're really just taking the 0. Then multiply by dx, right? Does that make sense? What happens here if you just multiply by dx? If you multiply dy by dx, don't you get dy? And this is your change in y. What should you change y by? Right? So if you multiply the change in y by the change in x, you'll get the change in y, yes? Now in this case, since dy dx was 0, multiplying by 0.5 gives me 0, so it says don't change your y by any. So go to your y, 1, and don't change it. And if you remember, that's what happened when we used the linearization formula. So this is my new y. Change your x by your delta x, 0.5. Bring your new y down, which of course becomes your old y, and plot that point. Now repeat the process. Go to the derivative with your new point. Plug in the derivative, and again for us that's only going to be 0.5. And I get 1. Multiply 1 by dx. That's how much I'm going to change y by. So what was my y? 1. Change it by 0.5. And get 1.5. Go down to your next row, change delta x by 1. You're going to use the linearization formula, plug in 1.5, but that's what you already did really here. So your new y is your next y, and you're going to plot this point, 1.5. Repeat. Take 1 comma 1.5 to the derivative, multiply by 0.5, take your old y, change y by 1, there's your new y. Your new y goes with your new x, which is 1.5. Plot. So now I'm just going to kind of... Now in reality, somebody will tell you where to stop. I stopped with 2,4, so I really didn't even need to do this. Right, I didn't need those numbers. So here I am. So these are, remember, linearizations. They're connecting, drawing my tangent lines between these points. Look what I get. Remember, we know the exact solution is x squared plus c with the initial condition, x squared plus 1, and there's the graph. So no, my linearization isn't exactly the solution, but it's an approximate. This is an approximate picture of the solution using Euler's method. And of course, the smaller dx you use, the closer your approximation will be. It always gets less accurate as you move away from the initial value. And now let's try this with a real differential equation that we don't know what it looks like. So this derivative is the one I gave you we first looked at, x minus y. I don't know what this solution looks like. And I can't solve this by any method that I know. So, given a derivative and an initial condition, remember this point is on a graph I can't see. But whose slopes I know. I know that the slopes on a graph I can't see. So, I'm telling you what your dx should be, 0.1, and I'm going to use Euler's method, and I'm going to organize my work in a chart. So here we go. Initial condition, 0, 1. Go to the derivative. This time the derivative depends on both x and y. Right, the derivative x, 0, y, 1, and I get negative 1. How did I get this again? Do you remember? How do I get that? You're taking dy dx, multiplying by dx, and my dx was 0.1. So multiply negative 1 by 0.1 and get negative 0.01. This is the change in y. So go to your y, which was 1, and change it by negative 0.1, and you get 0.9. 0.9 is the y coordinate of your next point. So this 0.9 is going to come here, and your next x comes from what? How do you get your next x? Right, you add delta x here. So 0.1, 0.9, repeat. Take 0.1 and 0.9 up to the derivative. Repeat. I'm only going to go through this 3 times, and then I can plot those 3 points, and I will get a very short picture of this graph that I can't see. So this is exhausting. As you can see, the numbers get pretty gross pretty quickly. There is the exact solution. Again, this is not a differential equation that you will be required to solve in this class, but it can be solved, just not by any BC calculus method. So this is what the exact solution looks like. And if you graph this, you will see how close these points are to it. When you plug in 0 and 1, of course, will be exact, and if you plug 0.1 into this equation using your calculator, you will not get 0.9, but you'll get darn close. Now, it is a little confusing when you look at this. You're like, wait a second. Are you telling me that if I take the derivative of this function explicitly in terms of x, if I take the derivative, that I'm going to get x minus y? That's what it looks like, and notice that the 0.01 is on it. And again, if you plug in 0.1, you will get something close to 0.9. But how did that happen? Right? Whoops, sorry. So how that happened, let's see. So let's take, we can do this, right? What is the derivative of y with respect to x? Well, the derivative of x is 1. The derivative of this constant goes away. The derivative of 2e to the negative x, right, is e to the negative x with that 2 in front. Chain rule, spit out the derivative of negative x and you just get a negative, right? Well, wait a second. That doesn't look at all like this, right? But this is y, is it not? So go up here and say, oh, what is x minus y? Right? So what is x minus x? X minus x is nothing, right? Negative 1 is positive 1, and negative 2e to the negative x is negative 2e to the negative x. There you go. Alright, so again, you saw on the warm-up slide that there was bookwork to go with this. You certainly use your calculator as things start to get gross. This is very algorithmic. There are programs out there that you can just plug in and it'll generate all the Euler's method. You plug in the derivative and the dx, and it will generate all these values for you. But these are going to be for AP. They're going to be on the non-calculator part, so the numbers will be easy. They will give you a delta x, and they'll tell you how many times to run through it. Or even if it is on a calculator portion, they're going to expect to see all this work. And they're only going to have you run through it a couple of times. Alright, I will see you guys on Monday. We're off to Whitetail to do some snowboarding. Bye! Nope, discard. See ya!